Morning, everybody. This is our live stream, first day of our school shutdown. So, unfortunately, I wasn't able to get the setup I was hoping for here. So we're going to be a little bit of sort of moving around a little bit, but at least we're here and we're up to something. I'm just going to share. Excuse me. I'm going to share the live stream for anybody who's waiting on the classroom. So just 1 second. How's everybody doing out there? Is there anyone out there? Want to give me a shout out? That'll be, and let me know you're there. That'd be great. Okay, I saw one person sort of kind of popping in there. Streaking there. Okay. So let's see where we're at. It's been a little while. Yes, okay. So we were just about to start talking about reaction mechanisms. That's what we sort of talked about on Friday, was the reaction mechanism. I'll try to do a sort of a condensed video, especially if this stream is not too popular. I might pause and do a more thorough or more a little nicer looking video at least for the last little while there. So with reaction mechanisms, we are talking about how in the case of a chemical reaction, it's not particularly, I'm going to put my headphones in just so make sure you're getting that full volume. Also, just in case so in a reaction mechanism, we are talking about, the idea that if you have more than two atoms that have to collide, once you have three atoms colliding, it's very unlikely that all three will hit at exactly the right angle that the reaction will happen. It might be possible, and in fact, one of the things that sort of comes out with reaction mechanisms is the idea that there are multiple ways that you could achieve the same chemical result. So that is so there might be competing mechanisms. Everything is quite fluid in the reality of things. But the idea is that the more complicated your chemical reaction is, the more steps are involved, and every step is about one bond breaking, one bond forming, give or take. And if we add those all together, excuse me. If we add those all together, then we should get a chemical reaction sort of sequence. So let's look over here to ozone. So this is what's going to be really my least fun part. Would love to just be able to, do this in a way that wasn't so janky, but okay. So in the case of ozone, up here, we have O2, so 2O3, two ozones become one oxygen. And how this probably proceeds is, if we try to think about this as breaking one bond at a time, what we have is so breaking and making one bond, maybe maximized one bond, breaking one bond, forming at a time. We're going to think about sort of ozone, which looks kind of like this. I think there's like sort of a partial double bond there. So this ozone molecule actually is going to break apart first, leaving our oxygen plus an oxygen atom. And this oxygen atom is very reactive. And so then this oxygen atom finds another ozone molecule. I'm going to draw it backwards this time. And then it's able to sort of attack it with its electrons, and these will break. So maybe I'll draw this. It's a little too organic chemistry. So we're going to draw a little bond forming there, and then the result is we're going to get 2 more oxygens on this side. So in this way, what we're trying to say is that we're going to get O3, which has a tendency to just break down into O2 plus oxygen, and then those are going to come back together. This oxygen that's free, this or a free oxygen atom, is going to find an O3 molecule, and then that's going to form 2 O2s. And so when we add them together, we can see that the O3s add up on the side. There's 2 of those, so we get 2 O3. Meanwhile, the free oxygens get canceled out because there's one on the left, one on the right. And then there's 1, 2, 3, 3 oxygens on this side, like so. Let's see. There we go. Okay. And so whenever we have a product that that almost immediately gets used up as a reactant, we call this a intermediate. So that's our intermediate. Well, in this chemical reaction, one of these steps is slower than the other. No 2 steps are equal. Remember that chemical reactions are um, and their rates are based on the nature of the chemicals. So my guess, I don't know this for sure, but my guess would be that this would be a slower step. You'd essentially be waiting around for O3 to find the right amount of energy to spontaneously split in half, or well, 2/3, 1/3. So this is a somewhat unlikely event. Excuse me. These early morning classes can be hard, even though I used to be up for every morning class. Um, so the O3 splitting is going to be fairly based on sort of a random event. It's going to be it will be slow and occurring randomly. Meanwhile, once you have a free oxygen, this is an incredibly reactive species, and so it will hunt out, or it'll be very active, moving around very quickly, trying to find a partner. And so this step of the reaction should be fast. And this informs us something about how the chemical rate is impacted by the various amounts of chemical that's being added. For example, in this chemical reaction, we might expect that the rate changes a little bit less quickly than we might expect when we add O3. Look based on the chemical equation, which says that there's 2 O3s in this chemical reaction. We might expect that this 2 has some sort of impact on the chemical rate, but in fact, we won't have that because it'll be a little bit slower, because the chemical reaction that this depends on only has a stoichiometry of 1O3. Okay, well, I'll get into that in a second. That is not going to be completely clear yet. So let's go to the rate determining step. So I'm just going to talk about it here while I type it out, and then I will display it. Okay. All right. So the rate determining step. This is the step of the chemical reaction. Out of the reaction mechanism, this is going to be the step that is the slowest. And because it's the slowest, it can hold up the chemical process. Any steps of the reaction mechanism that are faster are going to be faster, so that they will finish so much faster than the rate determining step that really we're only going to be waiting on those specific rate determining molecules to interact. So in the case of this ozone reaction we were just talking about, ozone is somewhat stable. So its stability implies that it's not very reactive. We have lots of ozone in our atmosphere. It's not nearly as reactive as oxygen, but it is not particularly reactive. So we are going to be waiting for a certain amount of energy to get into one of those ozone molecules to cause it to break apart. So possibly the result is that we want to think about the energy diagram. What does this energy diagram look like for this chemical reaction? I'm going to assume that ozone breaking down is exothermic or endothermic. I think it's an exothermic reaction. So I'm going to put my ozone over here, and then I'll show you what this looks like in in a second. I'm just going to draw it again one more time just until I'm happy with it. Okay, I bet you're all sitting there on pins and needles wondering what I'm drawing. Okay, so this is what I drew. So this is what I want to attract your attention to. So look, this is the potential energy diagram for this ozone breaking down. So notice this large activation energy hump as we take an ozone and break it down into an oxygen and an O3. Now this is a little bit tricky. Maybe I should put my O2 in there as well. Yeah, O2 like that. Yeah. So to convert that first oxygen into an O2 and an O, I have an initial high energy hump. And then that O3 and that oxygen, they have a lower hump. They have a lower activation energy. So they're going to react a lot quicker, and then all together we're gonna have three O2s. So these transition states, these points between chemical reactions, those will have little tiny plateaus inside the potential energy diagram. And each one will have their own little energy bump or their own activation energy to move to the next stage. Sometimes they'll be reversed. Sometimes the next stage will have the higher bump, the higher activation energy. Sometimes sometimes it'll be like this, where the first step is the higher one. Wherever the highest amount of energy has to go in, that's our activation energy. So let's write out a little rate determining step explanation here. So I'm going to get into that right now. My type stuck up really high. So the rate determining step of a chemical reaction is the slowest uh, slowest step in the reaction mechanism. Typically, just so I leave myself a caveat to be wrong, typically this implies that this step has the highest activation energy i.e. it's the least likely to occur. Now, reaction mechanisms, the rate determining step definitely does occur, right? It's just that it's less likely. So I'm just put a little bit of arrows on my diagram here, my activation energy 1, and then here's my. So there we go. And there we go. Okay, so did a little bit of drawing on my diagram here. So over here. So I'm showing now that the activation energy barrier is much higher for this first step. So this is step 1. Let's get a different color pen. So this is step 1. And then this is step 2 of my 2-step reaction, 1 and 2. 1 and 2. And so then this is the statement I want you to take note of. The rate determining step of a chemical reaction is the slowest step in the reaction mechanism. Typically, this implies that this step has the highest activation energy, or energy barrier, another word we might use. Any questions for you out there? Feel free to put that in the chat. I don't know who you are, I just know that there's one of you. Be right back, give me 1 second. All right, so if you need, you can always pause and go back. Let's get to the next part here. So in the next example, we're given, in the next page, we are given a 3-step reaction. And in that 3-step reaction, one of the steps has been identified as being slow. So let's look at the net reaction together. So let me see if I can set this all up so that it works together, so I can do this at the same time. Okay. Certainly not the most beautiful setup in the world, but it will work. Okay, so the net reaction, we can do that together. So let's see, we see a transition product here. So this is a transition, or an intermediate, sorry, that's what we're calling them, intermediate. So an intermediate. We see T show up over here, but it stays on the side. We see P gets used up, and but there's another intermediate, so this is another I. And then we have an R. Okay, so let's add them together. So we got a P on this side. There's 1, 2 of them. There's 2 P's. There's a Q. There's an S. And we already canceled out the other 2. And then we get 1, 2 T's. and we get an R. How's that looking? Okay, it looks okay for me. Let's see if we can just convert that to text. Well, that's a little bit weird. Okay, let's go to P and Q. You know what? Let's just cancel Q. Okay. What are the reaction intermediates? So we identified those as we went. I'm going to change to a pen that I can see. So the reaction intermediates were X and Y. And then what is the rate determining step? So we can see the rate determining step here is P plus Q goes to X plus T. So these are all going to be sort of, simulated chemical reactions for the most part. Chemical reactions are, as I said in class, very, very difficult to analyze and very difficult to collect. Reaction mechanisms, that is. But we do have a couple of them that we can look at. So there's something interesting that happens here, right? Because we have a chemical reaction up here that has P, Q, and S as reactants. So we would think that changing the amount of P or the amount of Q or the amount of S would all have effect on the reaction. But notice that S is not represented in our rate determining step. So if S is not in our rate determining step, it has no impact on rate. So what would the effect of increasing the concentration of P be? So if we increase concentration, we increase rate. So rate goes up. What would be the effect of increasing concentration of Q? Well, we see Q in our rate determining step, so rate goes up. What would be the effect of increasing S? Well, in our rate determining step, since this is the step that determines rate, we would have no effect. And that's really the big takeaway from this unit. So this unit particularly, or this lesson, is that if you have chemicals that are not in the rate determining step, they do not have significant effects on rate. S probably has a very tiny effect on the rate because it does impact the other steps of a reaction. But when we consider this effect, it's going to be a lot less than we would expect if we change P or Q. P or Q rates have been identified as being slow. That means they have very high energy barriers. And meanwhile, S and P, S is is only part of a final step that has still a moderate rate. So we could maybe no effect is an extreme no effect. I'm going to say no effect. I want to make a hard line that if it's not in the rate determining step, it's not going to have an effect, not an appreciable effect. Okay, so we do have some practice questions. I'll probably try to fill these out in the next little while and then upload the lesson. And then we are going to get into the next parts. Wow, we still got quite a bit to go through. What are we at right now? 9:30. Okay, so I think maybe I'll assign let's assign the practice section for right now. And I'm going to stop the stream and let you work on the practice. I'll work on it myself. And when you go to check the file on Google Classroom, it will be updated with the answer key. So you can go take some time right now before it updates on Google Classroom. Do these questions, and then tomorrow, if you want to type me a question in the chat, or if you want to send me a message in Google Classroom, you can just drop one in the stream, or put it as a comment on something on even this file. Then I will answer those questions there as well. All right, best of luck to you. Stay safe, stay socially distanced, and have yourself a good day.